Hi, everyone. This is the Modelers Community of Practice meeting for April. Thanks, everyone, for attending. I think the participants list is right on the edge between too many to intro. And I think in the interest of time, I'll ask everyone to introduce themselves in the chat. And we'll go from there. Okay, so today we'll be talking about Arctic amplification. As part of the Biennial Implementation Plan, IARPC and US federal agencies are tasked with advancing understanding of Arctic amplification and the associated connections with lower latitudes. The purpose of this meeting is to highlight recent work in this area. Previously, we have highlighted the Polar Amplification Model Intercomparison project. Those talks looked at the general response of Earth system models to Arctic sea ice loss, as well as mid-latitude impacts. So today, I think we're going to hear a more fundamental take on Arctic amplification drivers with today's presentations. So let's begin with the first presentation. That's by Nicole Feldl. She's an associate professor in the Earth and Planetary Sciences Department at the University of California at Santa Cruz. And the title of her talk is Icy, Moist, and Seasonal Polar Amplification in Idealized Climates. Nicole?
Right. Oops. Can you all see my slides?
That's good.
Wonderful. Thank you, Richard, for the introduction, and thanks for the invitation. I'm really happy to be here and to share this research with you all today. So in this talk, I'll be presenting research that uses idealized models to isolate the role of sea ice loss and water vapor increases in driving seasonally varying polar amplification. This work comprises two papers. So one is in collaboration with Tim Merlis, and the other is led by UC Santa Cruz PhD student Po Chun Chung. So polar amplification, of course, is the phenomenon of polar warming that's 2 to 3 times the global average. It exhibits quite a bit of spread or uncertainty among contemporary models. It's a wintertime phenomenon, despite the fact that sea ice loss and the associated ice albedo feedback are greatest in summer. You can see that in this plot, which shows in 4 different reanalysis data sets, a surface-based warming that peaks in late fall, or ND, November, December. And it's been attributed to the ice albedo feedback, the lapse rate feedback, and moist atmospheric energy transport, which I've circled on this plot. Now, when we look at a diagnostic plot like this, it suggests the processes are independent, though of course they're not. So a lot of my recent work the past few years has been in understanding the relationship between the ice albedo feedback and the lapse rate feedback. In the research I'm presenting today, I actually want to focus on moist atmospheric and sea ice processes and how they interactively govern polar amplification. So our approach is to use simplified models with thermodynamic sea ice. This is distinct from previous idealized studies that incorporate an ice albedo feedback only, but with no ice thickness, and so no insulation effect. So ice thermodynamics is included by calculating the temperature at the top surface of the ice from a balance between the conductive heat flux and the surface energy flux, where the conductive heat flux, as shown in the schematic on the right there, is just a simple linear function of ice thickness. So still fairly simplified. The surface albedo depends on temperature, and we investigate 3 different levels of atmospheric complexity. So in the EBM, or energy balance model, divergence of atmospheric energy transport is proportional to the meridional gradient of moist static energy. This parameterization permits an increase in poleward heat transport due to the preferential increase in tropical humidity with warming. And this would be distinct from a more classical dry EBM. In the gray radiation aquaplanet GCM, atmospheric energy transport is by the resolved large-scale turbulence. However, radiation is idealized, and in particular, there's no water vapor feedback. And then the comprehensive radiation aquaplanet GCM does have a water vapor feedback. However, I want to point out that none of these models They don't have continents. They also don't have clouds. So I'm really happy that Ivy is also in the meeting today, so we can have her expertise. So despite the different representations of atmospheric dynamics, the amount of polar amplification is comparable between the EBM and the GCM, 3 to 4 times more warming in polar than tropical regions. So the greatest annual mean amplification occurs for the case of a simple ice albedo feedback. And then polar amplification is reduced by the presence of ice thermodynamics, slightly reduced, shown by the gray line, and further reduced when there's no ice at all. Now, despite the fact that that effect on the annual mean is fairly small, the seasonal pattern of polar warming is really profoundly influenced by ice thermodynamics. So here I'm showing the seasonal pattern of warming for the case of a simple ice albedo feedback, where the surface albedo just depends on surface temperature, versus the case that actually does include a thermodynamic sea ice model. You can pick your favorite model to focus on. They both do the same thing, but you can see that the inclusion of ice thermodynamics produces this strong wintertime warming maximum and summer warming minimum. And the sea ice, or the simple ice albedo feedback, gets the seasonal warming pattern entirely wrong, with a summertime maximum that's inconsistent with observations and with comprehensive model simulations. So this demonstrates very clearly that ice thermodynamics is crucial for capturing the seasonality of polar amplification. Now, we expect that in addition to sea ice loss, an increase in moist energy transport contributes to polar amplification. And one place where the EBM really shines is that it's quite simple to turn off the effect of latent heat on the polar energy transport. And when we do that, we can see very clearly that polar amplification is nearly halved by disabling latent heat transport. So the plot on the left is that annual mean polar amplification that I showed in the previous slide. And the plot in the middle is a series of identical simulations, but these diffuse sensible heat rather than moist static energy. So going back to a more classical EBM style. And what you can see is that adding the moist energy transport roughly doubles polar amplification, whether or not you start with ice, and adding both ice and moisture together roughly quadruples polar amplification. The plot on the right summarizes the previous two by plotting polar amplification in the moist EBM against polar amplification in the dry EBM. This is just another way to look at what I just walked through, but you can see that all of the simulations are falling nearly on the 2-to-1 line, indicating that the effects are nearly additive in this model. So that was a pretty simple model, and to more thoroughly investigate the mechanisms, we perform a decomposition using 8 different GCM simulations. These have various components of the climate system that have been disabled or locked, so including the water vapor feedback, sea ice fraction, and sea ice thickness together. All of these are subjected to a 4 times CO2 radiative forcing, and then we can kind of isolate the response to these different physical mechanisms. And so these are plots of seasonal warming, and they demonstrate very clearly. So you can see this winter amplified warming in the total response, which is the plot in the top left. And this is primarily due to sea ice loss, and in particular to sea ice retreat. Sea ice thinning does make further contributions, so to both wintertime warming and summertime cooling. Whereas if you look up at the response to CO2, which also includes temperature feedbacks, as well as the response to the water vapor radiative effect, these two produce a seasonally symmetric polar amplification. So if we then focus on the seasonal asymmetries, which are associated with sea ice loss and shown in the bottom row, and perform a feedback analysis, we can see that the winter amplified warming is shown in the black dots. So this is the surface temperature change. The fact that it plots to the upper left of this 1-to-1 line indicates that it's a winter amplification of surface temperature. And we can see in the total response, this comes from a balance of 3 different terms. So we have the ice albedo feedback in cyan, the dry atmospheric energy transport in red, and the surface energy flux change in green. The same mechanism can be traced to the response to sea ice loss, where we see the same balance of 3 terms, and further to the response to sea ice retreat as well. So physically, what's going on is that ice retreats in summer, increasing the absorbed solar radiation. The excess heat is stored in the ocean and then released back to the atmosphere in winter, causing the winter warming and then that decrease in dry atmospheric energy transport. Now, interestingly, when we look at the response to sea ice thinning, this mechanism is short-circuited. So it's short-circuited when ice thins without retreating. Without ice retreat, there's no positive ice albedo feedback, and the surface energy flux response in winter is smaller. It still causes winter amplification, but it's a smaller effect, and it's instead governed by changes in conductive heat flux through the ice and the latent heating of melting ice. The change in dry energy transport is straightforward to interpret in terms of the change in meridional temperature gradient. So these large decreases in dry transport in winter that we see, so the big blue areas in the mid-latitudes, this occurs in response to the warming induced by sea ice loss and specifically sea ice retreat, with smaller contributions from sea ice thinning. There's also an increase in dry energy transport during summer that's due to the latent heating when sea ice thins. So this suppresses summer warming and then increases the meridional temperature gradient rather than decreases it. And you can see that signal propagates in the total response as well. So as noted on a previous slide, the temperature response to the water vapor radiative effect produces a small amount of polar amplification that is seasonally symmetric. And so here in the upper right plot, we can see that that's because of a balance between the increase in moist energy transport in winter, shown in blue, and the water vapor feedback in summer, shown in green. The plot on the right illustrates the physics here a little bit better. So here we're looking at the change in specific humidity and DJF. Since this is an aquaplanet, the southern hemisphere is the summer hemisphere and the northern hemisphere is the winter hemisphere. And so it's apparent that a strong increase in summertime humidity is consistent with an increase in the meridional humidity gradient in the winter hemisphere. And so that explains why these two terms are balancing one another, or they're linked together. And then here we can look at the full seasonal cycle of moist energy transport changes that indeed shows that the largest changes occur in response to the water vapor radiative effect. These changes are largest in winter. And this pattern is also the largest contributor to the total changes in moist energy transport. And so then in conclusion, I've shown here that the idealized modeling experiments show that the primary mechanism of wintertime polar warming, so this enhanced seasonal ocean heat exchange, is instigated by summer sea ice retreat. Sea ice thinning also enhances winter warming by increasing the conductive heat flux through the ice, as well as suppresses summer warming due to the latent heating of melting ice. Thus, both seasonal ocean atmosphere energy exchange and the the sea ice thermodynamics promote seasonal polar amplification that's strong in winter and weak in summer. The winter warming is further amplified by atmospheric feedbacks and then damped by the decreased atmospheric energy transport. And then interestingly, water vapor produces a seasonally symmetric polar warming by these offsetting effects. So an enhanced moisture in the southern hemisphere induces the summer water vapor feedback and simultaneously strengthens the winter moist energy transport in the winter hemisphere by increasing the meridional moisture gradient. So thank you very much for your time, and happy to take questions if this is the time when we do that.
Thanks, Nicole. So if you'd like to ask a question, I would suggest raising your hand and then I can call on you. That seems to be the easiest format to do. I have a couple of comments. One is that I work a lot with atmospheric reanalyses. Atmospheric reanalyses have almost no representation of sea ice thermodynamics. That seems to suggest that if in future coupled reanalyses, you would see a greater Arctic amplification feature than currently seen in reanalyses. I think in reanalyses, the amplification is driven mainly by observations going into the reanalysis system rather than the model showing the correct feedbacks. Would you agree with that?
That's a fantastic point. I'm really glad you brought that up. And yeah, I haven't worked too much with the reanalysis products, but I agree that if they're not representing, I mean, I think that the sea ice concentration is probably more important. The sea ice thickness, I think what I have shown in these idealized experiments is that it is contributing to kind of the having more winter warming and suppressing the summer warming. So I would expect there to be an effect there.
Okay. I think the other comment I had was with regards to the latent heat advection, which showed the large effects in the wintertime, but also the symmetric or the symmetric effects in the aquaplanet. So the real planet, of course, is not symmetric. Yep. What do you think the effects are? What does that introduce?
Yeah, so hemispheric asymmetries, you're right. Antarctica is very different from the Arctic. I would say that the results that I'm showing here are probably a closer analog to the Arctic, because I think when you introduce a large continent with a lot of topography, that's certainly going to change things. There's some really nice work by Lily Hahn talking about the hemispheric asymmetries in polar amplification. And I think that, I mean, we know, I didn't focus on the lapse rate feedback today, but we know that the lapse rate feedback is very important for this phenomenon. And I think that that has some of the asymmetries would be coming from that feedback, which makes sense because you have over Antarctica, you have a different depth of your inversions, how that's interacting with the atmospheric heat transport, kind of at what altitude in the atmosphere that heat is kind of being injected over the polar region makes a difference. So I think that a lot of that would be in the lapse rate feedback, but of course, all these processes are interactive for sure. But since I'm focusing a lot here on sea ice loss, I would probably draw the connections between this work and the Arctic more.
Okay. Vladimir, you have your hand raised. Would you unmute and ask your question?
Nice talk, Nicole. So I think I will probably make a comment about how clear separation can we actually kind of have between atmospheric heat transport and water vapor feedbacks in the Arctic. How local is moisture in the Arctic, especially in the winter,
Sure. Yeah, I think that's a great question. I mean, I think that I'm not sure that I have a complete answer to that question right now. It's something that that I'm future.
I don't think anyone has.
Yeah. Yeah, fair enough. I think though that so this is kind of a step into trying to get into that direction, is just by noting that, of course, if you have a transport of water into the polar regions, you can have from atmospheric energy transport that doesn't just condense and produce heating. You also have the water vapor feedback, of course, is going to influence clouds as well and various cloud feedbacks. So certainly all of these processes are interactive. And I think that, I guess one baby step in that direction was looking at, the way we've done this decomposition of all these simulations here is to kind of try to combine water vapor, the water vapor radiative effect, and thinking about the different seasonal characteristics. So I guess what we're seeing here in this plot in the upper right is that the moist energy transport and the water vapor feedback seem to dominate in different seasons. So there's not much the warming from the water vapor feedback in winter when the moist energy transport is largest is very small. So there's a seasonal difference there, but I think that there's certainly a lot more to be understood.
One other thing is that probably it's safe to state that all of those feedbacks are tightly coupled and they are acting non-linearly. There's no linear assumption that can be made. That's another problem that not so many people are addressing.
Thanks for your question, Vladimir. Hi Long, you have your hand raised. Would you unmute, please?
Yeah. Thank
Good to see you.
Nicole. Yeah. I'm actually at EGU. It's pretty late now. So yeah, thank you for a nice presentation. It was a nice discussion. I also feel very interesting about the water vapor result, but I will refer to a paper to learn more. But I have a quick question about the sea ice thinning experiment. Do you consider, you mentioned the conductive heat fluxes, but do you consider snow on top of sea ice, any change to snow albedo? And maybe some male pond, that kind of treatment?
That is a very good question. Those effects are not in these results that I'm sharing today. So I have another project that is doing something kind of similar, but in CESM. And in that case, we are considering snow thickness, melt ponds, and so forth. But I don't have those results ready to share right here. So in this case, we're just kind of, this is a simpler model. So in this case, it's just ice. And sorry, I was just seeing if I could flip back to that. But in this case, it's just ice, not those other effects. So good point.
Right, thank you. Yeah, it looks like we can have you back in a few months to report that.
I'd love to.
Thank you.
That's a good point. I had thought about the snow cover as well. I think modelers have focused a lot over the last decade on snow cover on sea ice and the conductivity associated with that. So this suggests that that's very important for reducing uncertainty in Arctic amplification.
Yeah. Also, I mean, there's so many, you know, once you kind of build up in complexity, yeah, your snow grain affects the albedo very strongly. So it's definitely important to consider as well.
And Wilbert, you have your hand raised.
Right.
Yes, very nice presentation, Nicole. Really enjoyed it. Can you tell us a little bit about the treatment of the ocean in your experiments?
That is an excellent question, and I should have said it. So in these particular experiments, in the GCM experiments, 0 Q flux. So it's just certainly no ocean model and no representation of ocean heat transport. And certainly, I think that that's very important for representing polar amplification and for getting kind of one side comment I can make on that is that I think that having even just a Q flux, but something that represents a realistic ocean heat transport, I think that's really key to getting polar amplification because of the way that those ocean atmosphere heat fluxes interact with clouds. So I think that's a very important effect that we weren't exploring here. But I think that some of the results that show a complete lack of polar amplification in simplified models can be traced back to how they're representing the ocean heat transport.
Right.
And that's something that we've been looking at that very carefully. Yeah.
Right. Do you have a prescribed mixed layer depth distribution or something?
It's uniform. So I think with sea ice, you have to make sure it's pretty deep because you can't have you can't have the ocean having too low of a heat capacity, or your ice will grow too much and shrink too much. So it's 60 meters, I think, in all of these.
Okay.
60 meters everywhere is my mixed layer depth. Yes.
Right, and no seasonal variation in that.
No seasonal variations in mixed layer depth, but all of these simulations have a seasonal cycle of insolation.
Thank you.
Yeah. Yes.
Thanks for the clarification.
And Renew, would you unmute and ask your question?
So maybe I haven't understood it fully, but this seems to be a zonally symmetric model, right?
Correct.
Is there a way that you could bring in some asymmetry, and what I'm trying to get at is, can you think of a way that you can potentially use this, or maybe a little bit more of an asymmetric model to understand atmospheric rivers and its contribution? And how would you do that? I mean, are there people doing that? Just a question. Yeah.
Yeah, that's an interesting question. I think I've thought about this a little bit. You can add idealized continents. So certainly people who have been looking at kind of putting in idealized continents to understand the monsoon in a very similar type of aquaplanet setup. So you can do stuff like, changing the evaporative resistance of these idealized continents to kind of more mimic land. I think that could be really interesting for looking at atmospheric rivers. I'm thinking more about just going one level up the hierarchy and actually including realistic continents, because I imagine that the shape, I think there are definitely some really interesting questions that could be asked with the more idealized continents, but I think that my own plan is to look more at realistic continents and then how that would affect some of these moisture transports. But I think I love idealized models, so I think that could be pretty neat too.
Thanks.
Mm-hmm.
Okay, thanks, Nicole. Let's go to our next speaker. Our next speaker is Ivy Tan. She is an assistant professor in the Department of Atmospheric and Oceanic Sciences at McGill University. I should add that IARPC has an objective to support coordination and engagement with federal, international, and non-federal partners. So we're pleased to have Ivy present from McGill University. Her title is Ice Nucleation and Arctic Amplification.
Hey, can you all hear me well?
Yep.
Okay. So thank you for the invitation to speak today, and it's a pleasure to be here. So I'll be presenting the results of two studies that highlight the impact of ice nucleation on Arctic amplification and large-scale climate models. I'll also discuss at the end some lessons to be learned from these studies. So I don't think I need to belabor this point to this audience, and especially after Nicole just gave her a nice presentation, but just to stress that although climate models agree that there will be Arctic amplification and it's occurring and it's continuing to occur, they still largely disagree on the extent of that warming. And so you can see that nicely here in this plot of the zonal average surface air temperature on the right here, where each line represents a single climate model, and the fact that the lines are more spread apart in the Arctic than elsewhere. And so many studies in the past have shown that clouds play an important role in the Arctic radiation budget, and therefore Arctic climate change. And so one of the very common types of clouds that you see in the Arctic are mixed phase clouds that consist of both supercool liquid droplets and ice crystals. And many of these clouds in the Arctic tend to be stratiform. So the typical structure of these clouds in the Arctic tend to take on this unique vertical structure where there's a thin supercooled layer at the top here, which is shown in this, it's shown by this high LiDAR backscatter in the bottom panel here. And then also with ice precipitating below it, shown by this high ground-based radar reflectivity in the top panel. So because mixed phase clouds exist at temperatures below what's required for, above what's required for spontaneous freezing, the ice crystals in these clouds, they mostly rely on aerosol particles known as ice nucleating particles or INPs to initiate this ice forming process. And so there are 4 different ways in which this can happen. But it's argued that the most atmospherically relevant ice nucleation mechanism through which ice formation in mixed phase clouds happens is through what's known as the immersion freezing mechanism. So this is where you already have an INP here that's immersed in a liquid droplet before it freezes. And so this is another plot that Nicole has shown, but now I'd like to focus on the clouds and in addition to the albedo feedback in this plot. So we've long known since the 1990s that clouds represent the largest uncertainty in climate projections. And so the problem still plagues us today, not just for global climate predictions, but also specifically in regard to Arctic amplification. And so this paper by Han et al. Nicely shows this for both the previous generation of CMIP-5 models and for the most recent generation of CMIP-6 models aligning with the IPCC 6 assessment report. And what I want to highlight from this plot is that the CMIP-6 models showed more Arctic warming than the CMIP-5 models. And this was attributed to first a more positive albedo feedback, but also a less negative cloud feedback. So just focusing on the clouds now, in other words, clouds damp Arctic warming overall, but there's less damping in the latest CMIP-6 models compared to CMIP-5. And so this overall cloud feedback that's referred to here is essentially the result of a combination of many different changes in cloud properties. But given the ubiquity of Arctic mixed phase clouds, the property that is of particular importance is the composition of thermodynamic phase within the mixed phase cloud. So basically, how much liquid versus ice there is in the mixed phase clouds, and how that thermodynamic phase of the cloud changes in response to Arctic warming is known as the cloud phase feedback. So just to talk a little bit about how this feedback works. So if you have an initial warming perturbation, let's say if the Arctic warms due to a doubling in CO2, then the troposphere deepens and the isotherms also shift upward in altitude. So this means that statistically, you're more likely to replace liquid with ice with liquid. So instead of ice, you tend to have more liquid. And so because the liquid tends to be more reflective than ice for the same water content, this will cool the Earth's surface and therefore act as a negative feedback. So in other words, if you start out, if your pre-warmed state contains clouds that are icier, then what tends to happen is that they become replaced with liquid droplets, and therefore the cloud feedback is more strongly negative. It counteracts the initial warming perturbation. However, interestingly, at the same time, liquid clouds, so the liquid that is replacing the ice is also longer lived because it's less efficient at precipitating out. So at the same time, what you get is these longer lived mixed phase clouds that tend to emit more downwelling long wave radiation to the Arctic surface and therefore amplify Arctic warming, thereby acting as a positive feedback. So this contrasts with what is dominating globally. Globally, you tend to have this negative cloud phase feedback, but in the Arctic, you can have this locally strong positive feedback that gives very different results than the global average. And so now having motivated all of this, my goal is to summarize 2 studies that demonstrate how sensitive Arctic amplification is to ice nucleation. And I want to demonstrate this point using 2 different global climate models. One is the GEOS-5 model, which actually technically hasn't really been used as a global climate model. This is like one of the first times we actually tested it as a global climate model. And the other model is the CESM-1 model, the NCAR model. So in the first study, so first talking about the CESM model study. In this study, we perturbed simultaneously 6 different cloud microphysical parameters, one of which included ice nucleation, which is listed here at the top of the parameters that we perturbed. And so taken together, the perturbations to all 6 of these cloud microphysical parameters resulted in very different partitioning of liquid versus ice in the mixed phase clouds. And so you can see that here in these simulations, looking at the left-hand panel here, where a higher SLF means that there's more liquid in the mixed phase clouds, where you tend to have more liquid in the mixed phase clouds, your Arctic amplification tends to be smaller. And so you can see that essentially what's apparent from these 2 bar plots is that the amount of liquid versus ice in the mixed phase clouds is anti-correlated with the Arctic amplification factor. And so clearly the impact of cloud microphysical processes can end up having a very large impact on Arctic amplification in these global climate models. But in this study, we've perturbed 6 different cloud microphysical parameters altogether. And so, however, given the importance of ice nucleation for mixed phase clouds, a natural question to ask is what's the individual contribution of ice nucleation to Arctic amplification? And so this is what study number 2 using GEOS-5 addressed. So this model uses the Morrison, a variation of the Morrison and Gettleman 2008 cloud microphysics scheme that is also common to the CESM model that I just discussed. But in these simulations, what we did was to replace the immersion freezing mechanism in the model in 4 different simulations. And so these 4 simulations were run both in the present day climate state and then also in a climate warming scenario. So these different immersion freezing parameterizations showed a very wide range in the INP number concentration as a function of temperature. And I'm going to refer to this quantity as the INP slope. So basically it's the amount of ice nuclear particles you have to the ratio to the air temperature. And so out of these 4 parameterizations, the parameterization that had the steepest slope is the Ulrich et al. 2017 scheme, or the U17 scheme. And it turns out that this U17 scheme actually has an INP slope that's closest to airborne in situ observations that were taken at cloud level. And so I want to note, however, that it's very rare to find aircraft in situ observations of INPs at the cloud level. These were actually only available in the springtime, and so this comparison was made during that one season alone. So it turns out that this INP slope is very important because it means that when you have fewer INPs here, so if you consider, for example, this red curve with a steeper INP slope, it's got fewer INPs at warmer temperatures. And so what this implies is that at the warmer temperatures, you have fewer INPs and therefore less cloud ice and therefore a weaker cloud phase feedback. And it's possible that if there are so few INPs at warmer temperatures that your cloud phase feedback can actually shut down. And so the implications of this are that if you have a very weakened cloud phase feedback, during the summertime, when you actually do have shortwave radiation from the sun, that sunlight can actually penetrate through to the surface and melt sea ice. And so that will result in a larger albedo feedback. So just like the plots Nicole has shown, I don't really need to explain this here. Basically, the distance, from the 1-to-1 line is how much Arctic amplification occurs here. So you can see for U17 that albedo feedback is larger than in the Myers et al. Scheme, for example, which has a less steep INP slope. And so so it shows that when you have this weaker cloud phase feedback, you also tend to have a larger albedo feedback too. On the other hand, so if you consider the Myers et al. Scheme with the less steep slope, the clouds are basically shielding the shortwave radiation from melting the sea ice, and therefore you have a smaller albedo feedback. So in summary, there is a very large influence of ice nucleation on Arctic amplification via these interactions between ice nucleation and the albedo feedback. And in the context of the CMIP-6 models, the two schemes that we just saw here with very different IMP slopes, they have Arctic amplification factors that are so different from one another that they actually span 30% of the spread of the Arctic amplification of all of the CMIP-6 models. So in summary, the parameterization of ice nucleation and global climate models has a very large impact on Arctic amplification. And it's actually through the influence of Arctic sea ice. So there's a very strong nonlinear interaction between cloud and sea ice feedbacks. And it appears that a key feature of how important ice nucleation is related to how the INPs are distributed vertically in the atmosphere. And it turns out that the summertime is particularly important because this is a season where most of that sunlight is melting the sea ice. And so summer is critical, yet at the same time, we don't have cloud level observations of INPs to constrain their distribution in global climate models. So thank you for your attention, and I'll be happy to take any questions.
Thank you, Ivy. So again, if you have questions, please raise your hand and I can call on you in order. Just to clarify then, when you ran the GEOS5 model, this was the uncoupled version of the model, is that correct? Or did it have an ocean?
Yeah, so due to the time limitations there, I didn't say those details, but basically we ran both. So
You ran both.
there were these atmosphere only simulations, and there were also coupled simulations. So the atmosphere only simulations, all four were run. And so in the AMIP configuration, so it was like AMIP and then AMIP plus 4K, where the sea surface temperature was increased uniformly by 4 Kelvin. And then because of the high computational cost, only 2 of these with very different IMP slopes were selected to run in fully coupled mode. And so for those climate warming experiments, a quadrupling of CO2 was done for those. So the purpose of running both types of simulations is because with the AMIP, you can isolate the effects of only the cloud feedbacks, whereas with the fully coupled simulations, this is where you can say something about Arctic amplification and how robust those cloud feedbacks are in the atmosphere alone simulations without the fully coupled nonlinear interactions.
Okay. Hailong, you have your hand raised?
Yeah. Ivy, thank you for the nice talk. I wonder, when you study IMP, are you looking into those transported from lower latitude or maybe local from like marine organics or?
Yeah, that's a great question. So in GEOS5, that effect is not well represented. So there are many effects that that can have important influences, like the transport of low latitude aerosols. Also, when the sea ice melts, if there are any IMPs that are released into the atmosphere, those effects were essentially not taken into account in this study. So it's possible that if those effects are parameterized, that they may have additional effects that could also influence Arctic amplification.
And I have another quick question related to precipitation over ice or snow. So the other, the positive feedback loop, when you have less ice and more liquid, if they rain, it will be in liquid. So that could affect the surface albedo, especially snow cover. But that is a negative feedback, right? If you is that considered somewhere? Any work related to that?
Yeah, that's the first time I heard that one. So you're saying that if you have precipitation effects that you're also considering that they could warm precipitation that could melt sea ice and also feed back.
Yeah, it's like more like rain on snow could largely reduce snow albedo.
Right.
I think the coupled model would, because it has a version of CICE, and so it would show the snow compaction resulting from that and the lower albedo. The GeoS5 models don't have a representation of aerosol deposition onto ice surfaces, and that's something that we've thought about and some people have worked on, but it's very complicated, and so we don't have a representation of that yet.
But what I mean is more like rain on snow rather than snow snow on snow. So it's like reduced albedo is it's a cooling effect rather than the positive feedback.
Right.
Yeah.
This wasn't considered in this study, but that's another interesting nonlinear interaction that could feed back into this that wasn't considered. Thanks for your
Thank
question.
you.
So I just wanted to go to that result then from the first experiment then. So as you increase the cloud liquid water, then you have a reduced Arctic amplification. So can we say anything then about the long wave cloud forcing then? I would think that if you increase the liquid water, you might have an enhanced, downwelling long wave, but this would suggest that that's canceled out by other processes. Am I reading that right or not?
Yes. So the effect that you're referring to is related to the present state of the climate, where you have like a long wave cloud radial feedback. In this feedback loop, it's more about like when you have liquid in the mixed phase clouds, and then in response to warming perturbation, what happens is that the liquid or the ice, whatever ice is in the clouds, is replaced by liquid. So if you start out with a lot of liquid, there's essentially no replacement of ice with liquid that is possible. And so you get this weakened feedback here. And the role of liquid is to warm the surface. So, so in other words, if you start off with more liquid in the mixed phase clouds, that negative feedback is weaker. And so, so that means that at the same time that there's less downwelling long wave radiation that is also able to warm the surface as well. So yeah, so it's still related to the downwelling long wave feedback, downwelling long wave radiation effect, but it's through a feedback loop that happens after Arctic amplification occurs.
I see. Okay. Now, when you run the 2-moment cloud microphysics, I would imagine that you're running the go-kart aerosols and aerosol transport. So a lot of those values, of course, come from MODIS, which are visible sunlight detection of aerosols in the atmosphere. I don't know if there's that much known about aerosols in the winter over the Arctic, but I was wondering if you could make some suggestions about what type of observations would help cloud modelers for representing mixed phase clouds.
Okay, yeah, that's a good question. So specifically in terms of aerosols and their impacts on mixed phase clouds, then your question is more related to that?
Yes.
Okay, so yeah, I think with MODIS especially.
Well, just in general, how would you characterize the knowledge of aerosols over the Arctic as compared to other locations on Earth?
Right. Oh, yes. Very, very poorly observed. I think the major problem is the fact that the aerosols are very tenuous. And so even Calypso, maybe, for example, Lauren Zamora has done some nice work on that at NASA Goddard, that these aerosol layers are so tenuous that even Calypso is unable to observe them. Or sometimes they are confused with diamond dust. And so,
Oh, yeah.
right, so
Yeah.
it's definitely very difficult to characterize those tenuous layers. And so observationally, what would be helpful is to have more sensitive sensors that are more sensitive to tenuous layers. So that is that would be very useful. In situ observations can supplement with that, but of course they're very local in scale, and many of them are also only available at the surface as opposed to at the cloud level. And so I think having vertically resolved observations of very tenuous aerosols would be very helpful in this regard, in terms of better modeling aerosols and then also their impacts on mixed phase clouds as well. I also think that summertime aerosols are very much neglected. There are a lot of observations during the springtime and also during the fall. Those are the most common seasons where you have these field campaigns. But in the summer, I think there's a lack of observations that is kind of suggesting that, at least from this study, it's suggesting that summertime observations are also important. So I think having more observations in the summer would also be helpful, and just not to neglect that season.
Okay. Are there any other questions for our speakers? If not, these are two tremendous talks. I thank the speakers for their presentations. This was really great. I think there's something in the chat here. So our next modeling group meeting is something special. I was wondering if Wilbert could unmute and say a few words about that.
Sure. Thanks, Richard. So we're going to have a next meeting on June 1st, and this is going to be the first in a series of sessions on that address the tenacious biases in the Arctic Earth system in Earth system models. So the first session will be focused on the stratification in the Arctic Ocean, which is very much biased in most Earth system models. So we will have a 2-hour session, jointly organized in this case with the physical oceanography team. First, we'll have a couple of introductory presentations, and then we will have a panel discussion with representatives of the major U.S. Earth system modeling centers. So hopefully we'll be able to exchange some information on the causes, the root causes for some of these biases in Arctic Ocean stratification, and hopefully be able to identify a path forward, maybe a collaborative path forward to improve those biases. So that's going to be June 1st, 11 a.m. Mountain Time, 1 p.m. Eastern. And hopefully this will be the first of a series of sessions addressing different biases in the Earth system. And one follow-up session could be among clouds, the representation of clouds in Arctic Earth systems. Aerosols might be another one, sea ice or ice sheets. So that's still something to be determined. But the first one is going to be on Arctic Ocean stratification on June 1st. Thanks, Richard.
Thanks, Wilbert. So again, I'd like to thank the speakers. I'd like to thank everyone who attended and asked questions and participated with the modeling team. And I think that will do it. We'll see you again on June 1st. Thanks, everyone.
Thank you. Bye.
Bye-bye.